time, it's like this bedrock of reality, right? It marches on, unwavering. Same for you, same for me, same for that coffee cup over there.
Uh-huh. Yeah, seems that way.
But what if down in the quantum world, time isn't so straightforward?
Oh, things get really weird down there, that's for sure.
Exactly. You sent me this really interesting paper suggesting time might actually flow differently for quantum objects compared to, well, us larger scale folks.
Yeah, it's a pretty wild idea, isn't it, that quantum systems might have their own kind of internal clocks ticking away at a different pace.
That's what we're diving into today, this whole concept of differential time flow in the quantum realm.
Should be fun.
It should be. So the core idea, from what I gathered from the paper, is that measurement, like when we observe a quantum system, might actually be more than just passive watching. It might be forcing that system to sync up its time with ours.
Yeah, like we're imposing our own temporal framework on it.
Right, and before we measure it, who knows? It could be experiencing time in a totally different way.
And that could explain some of the weirdness we see in quantum mechanics.
So let's start with superposition. We know a quantum object, like an electron, can be in this blurry state of seeming to occupy multiple states at once before we measure it.
Right, like it hasn't quite decided what it wants to be yet.
This theory proposes that this superposition isn't just some inherent uncertainty in the electron, but rather a result of the system experiencing time differently.
Much faster, the paper suggests.
Like it's moving through its possible states super quickly, so to us it appears spread out.
And when we measure it, we're essentially forcing it to pick one of those states based on our much slower time scale.
It's almost like, imagine trying to watch a hummingbird in flight.
You just see a blur.
Exactly. To us, the wings are just this fuzzy mess, but to the hummingbird, each flap is distinct and clear. It's all about the frame rate.
So in that analogy, we're the slow motion observers, and the quantum system is the hummingbird zipping around in its own fast-forward time.
So measurement itself, as you said, becomes this act of synchronization. The paper even mentions energy exchange during measurement might be the key mechanism for how these different time flows get aligned.
Yeah, that's fascinating. It suggests that energy and time are even more deeply intertwined than we thought.
Which brings us to quantization, right? Those distinct energy levels in atoms. I mean, could those levels actually correspond to specific rates of time flow for the quantum system?
That's one of the questions this theory raises. It's like maybe only certain speeds of time are allowed for a given quantum system.
And what about the uncertainty principle? That always felt like this fundamental limit to what we can know about a quantum object.
Yeah, you can't precisely know both position and momentum at the same time.
Right, but through the lens of this new theory, it could be that when we try to pin down one property, like an electron's position, we're essentially forcing it to sync up to a very specific moment in our time.
Which then makes it impossible to know its momentum, which is linked to how it's moving, potentially very rapidly, in its own faster time frame.
It's like trying to grab a single frame from a high-speed video. You lose all the information about the motion between the frames.
It's a trade-off, in a way, between knowing where it is in our time and knowing how it's moving in its own time.
Okay, then what about entanglement? That spooky action at a distance stuff.
That's where this gets really mind-bending. The theory proposes that entangled particles might have their faster time flows, well, entangled.
So when you measure one, you instantly affect the other's time frame as well.
Leading to those seemingly instantaneous correlations that have always puzzled physicists.
It's like their internal clocks are somehow linked up, even across vast distances.
Right. And that connection happens through the shared faster time frame, not through our usual understanding of space and time.
And then there's wave-particle duality, that whole idea that quantum objects sometimes act like waves, sometimes particles, depending on how we look at them.
Yeah, that one's a classic head-scratcher.
This theory suggests that wave behavior might be what we observe when we're looking at a quantum system without directly interacting with it. So we're seeing the effects of that faster time flow playing out.
And particle behavior might be what we see when we measure it, forcing it to localize in our time frame.
So we're kind of imposing the particle-like nature through our active measurement.
Exactly. It all comes back to this interplay between different time flows.
But this is all pretty theoretical, right? I mean, there must be some huge challenges to actually proving any of this.
Oh, absolutely. The biggest one, as the paper points out, is figuring out the math. How do you describe these different time flows and their synchronization in a mathematically rigorous way?
We need equations we can actually test.
Right, the concept is there, but we need a way to quantify it.
The paper also mentions needing to determine just how much faster time flows in quantum systems. Is it 1,000 times faster? 1,000,000 times faster.
And does that rate depend on the system's energy, its mass, other properties? Those are all open questions.
Plus, what's the exact mechanism behind this time synchronization during measurement?
Is it purely about energy exchange, or is there something else at play?
And how does this new idea of quantum time flow fit in with Einstein's theory of special relativity, where time dilation is all about relative motion?
It's a lot to untangle.
It is. But the paper does offer some initial mathematical ideas, like maybe modifying the time operator in quantum equations, or introducing a new factor that describes the rate of time flow, something they call tau, I think. They even sketched out a modified version of the Schrödinger equation.
Yeah, and they showed that tau, the rate of time flow, could be related to the energy of the system, like higher energy, faster time. But there's this unknown constant, alpha, in their equation that links those two.
So finding a value for alpha, that's key.
Absolutely. That could be the missing piece to understanding how energy and time are fundamentally connected at the quantum level.
So to wrap things up, this deep dive has really taken us down a rabbit hole, hasn't it? It seems like quantum systems might experience time in a profoundly different way than we do, and that this difference might hold the key to solving some of the biggest mysteries in quantum mechanics.
It really challenges our assumptions about what time is and how it works.
And it leaves us with a really big question. What if time itself, down at the quantum level, isn't a universal constant ticking away at the same rate for everyone and everything?
Yeah, what if it's more like a dynamic property, something that can be influenced by energy? It makes you wonder how much of what we think we know about reality might need to be reevaluated.
It's definitely something to ponder.